In this video, you and I get to discuss, implement, and verify Group Encrypted Transport VPN, or as his friends call him, Getvpn. I'd like you to imagine that the phone rings, and it's this company called Acme Incorporated, and they would like to hire you and I to come down as consultants to work with them on some challenges they're having. And so as we get on site, they show us their topology. It looks something like this. They've got 4 routers, R1, R2, R3, and R4. They are currently using a service provider for wide area network connectivity between the sites. And regarding the MPLS services that Acme is using from the service provider, they are currently getting MPLS Layer 3 VPNs, which effectively means that each of these routers that are shown here are appearing with a routing protocol with the service provider. And then using the techniques of MPLS, the service provider is logically giving them connectivity between those 4 locations in the same virtual private network. Now, the VPN portion in MPLS Layer 3 VPNs doesn't imply encryption. It simply implies that Acme's traffic and Acme's connectivity between their sites is kept separate and private from other customers of that same service provider. And if you're interested in more detail on MPLS and that specific technology, come check out our MPLS course right here at CBT Nuggets. Now, as Acme Incorporated asks us our opinion regarding how to protect that traffic, what options do we have to offer? Well, we could offer DMVPN, where it could start off as a hub and spoke logically, and then we could build spoke-to-spoke tunnels. That's possible. However, we could also do that with FlexVPN, where the spokes dynamically connect, and then with the NHRP and the shortcut, they could redirect traffic directly between the spokes. Now, one of the challenges of that is that there is a little bit of cutover time. So if we had R2, R3, and R4 all connected to the hub, and then we need to have a cutover directly between R2 and R4, there may be a few milliseconds of delay or a few seconds of delay while the tunnel is being negotiated and brought up. So if we have active traffic going over that tunnel, for example, Bob, maybe he's using a voice over IP application, talking down to Lois, and if we lose a packet or two while R2 and R4 are negotiating and bringing up the tunnel, that may or may not be acceptable from a usability perspective between Bob and Lois if they're using an application that is unacceptable with packet loss. So using FlexVPN, what we could do is we could set up manual tunnels for everything. We could do a full mesh of manual tunnels. But the negative side of that is that there's a boatload of configuration to do. And in fact, if we were using legacy IPsec site-to-site VPNs with a traditional crypto map, we could also do a full mesh of site-to-site tunnels. But again, from a management perspective and the administrative overhead of doing that, that's not a very desirable solution. The other problem, even if we did put in a full mesh, is that if the customer is using a multicast application, let's say I have a multicast server right here, and Bob's a multicast client and so is Lois, so they want to both receive content for a specific multicast group. And let's say there's another user called Laura over at Site 3, and she also wants to go ahead and receive that multicast content. How is R1 going to get the multicast content to R2, R3, and R4? Unfortunately, it has to take this multicast content, which the idea is send it once to multiple destinations. But because we have these point-to-point tunnels in place, R1 is going to have to take that multicast traffic, encrypt it, and send it once over to R2, another time over to R3, another time over to R4. Unfortunately, R1 just can't send it once and then have the service provider network go ahead and deliver that because we have this IPsec overlay that's based on point-to-point tunnels that we have to send that multicast traffic over. So in the case of multicast, that is a bunch of replication regarding IPsec traffic that if we could avoid, we'd want to. Now the great news is this. If we have these 4 routers and they all have connectivity to each other, for example, over a service provider MPLS network, we could implement the technology called Group Encrypted Transport VPN, or as its friends call them, Getvpn, and that would solve the problem of having to do IP replication for multicast traffic before sending it off to 3 different sites. It would also alleviate the problem of a delay or loss of packets when R2 and R4 are going to start building a tunnel directly to each other, and that's because with Getvpn, R1 and R2 and R3 and R4, they don't need any site-to-site tunnels directly between any of them. And they can still send encrypted traffic to and from each other. One of the challenges in learning a new technology or a new method of doing things is a lot of the acronyms that are thrown out there. So what I want to do is walk through some of the ingredients with Getvpn, which stands for Group Encrypted Transport, so that we're familiar with the basic building blocks of Getvpn. It's also noteworthy for you and I to realize is that Getvpn is not the perfect solution for every type of topology. The default topology that Getvpn was designed to work on is a full mesh. To pull this off, we're going to use a single security association for IPsec. And with that security association, we're going to have a key for encrypting as well as for decrypting traffic. And there's the magic. If R1, R2, R3, and R4 are all using the same security association, and they have the same key for encrypting and decrypting the data, and then any traffic that's sent between R1, R2, R3, and R4 can be correctly encrypted and decrypted respectively. Now they have a special 3-letter acronym that identifies this key that's used to encrypt the traffic that's being sent between these group members. And that key is called the Traffic Encryption Key, or TEK. For example, if R1 is forwarding a packet destined to the 10.3.3 subnet and sourced from a device on the 10.1.1 subnet, R1 will say, I know exactly what to do. I need to take that packet, I need to encrypt it with the traffic encryption key, and then go ahead and forward it. Another interesting aspect of Getvpn is that the original IP header, for example, if this packet came from 10.1.1.6, a host on that subnet, and it was going to 10.3.3.9 on the far subnet, the IP header is going to be preserved. And so as the packet's being forwarded across this MPLS network, if we eavesdropped on it right here, it would show a source address of 10.1.1.6 and a destination address of 10.3.3.9. So it preserves the IP header. And the recycling, if you will, or the reuse of the existing IP header is not something that we traditionally do. In traditional site-to-site VPNs, R1, if it received a packet from 10.1.1.6 going to 10.3.3.9, it would take that packet, encrypt it, and then shoot the packet over to its peer at 35.0.0.3, and that would be the outside IP header that would be seen across this network. And then R3, the peer of R1, would typically decrypt that and then forward the naked clear text packet onto its destination. And again, the difference with Getvpn is that we are not going to modify the IP header. We're simply going to forward it with the original IP header. So this also implies that our service provider network, or whatever it is that's gluing these 4 sites together, or these 4 routers together, it needs to have the routing capability in this cloud of reaching the 10.3.3 network and the 10.1.1 network directly without those IP addresses being hidden inside of IPsec. Because again, with Getvpn, the original IP header is going to be used to actually forward the packet from source to destination. Now behind that IP header, we still are going to be using ESP, which is protocol number 50, which is the encapsulating security payload used by IPsec. And as part of ESP, there is a little ESP header that has the security parameter index, which is going to indicate which security association we're using for the appropriate decryption of that traffic. So now the good news is that if we have this multicast server and we're forwarding traffic to some multicast group, R1 can simply forward that as an encrypted packet, maintaining the original IP header, and the intermediate network, if it's enabled for multicast forwarding, can go ahead and forward that to the correct destinations it needs to go to. So instead of R1 having to encrypt and forward that 3 different times, the multicast traffic, as intended, can be encrypted, sent once, and then delivered to the respective routers who need that multicast traffic. So the same traffic encryption key, or TEK, is going to be used by the routers who are participating or playing the game of Getvpn. We also have a special name for routers that are participating as part of Getvpn, who are doing the encrypting and the decrypting. And they call those members of this Getvpn group GMs, or group members. So in this topology, for example, on the MPLS network that connects all these routers together, R1, R2, R3, and R4 could all be acting as group members, which means they're all using the same traffic encryption key. And another way of saying that is saying that they're all using the same group security association. Now, one of the key ingredients that makes this all possible is that each of the group members is buying into and they believe and are using that common security association. And the actual protocol that helps define all this is called GDOI, which stands for Group Domain of Interpretation. So whenever you see the term Group Domain of Interpretation, or GDOI for short, just think about the concept of a bunch of routers all buying into and believing and using a common security association and a common traffic encryption key as they encrypt and decrypt traffic respectively. Now, one of the challenges we have with Group Domain of Interpretation in Getvpn is how do these group members, R1, R2, and R3, and R4, how do they know the answer to the magical question, should I encrypt this or should I not encrypt this? For example, if our user here, Bob, is sending traffic out to the internet, should we encrypt that traffic or should we let that go clear text? If Bob is talking to a device over on the 10.3.3 subnet, should we encrypt that or should we just send it off in clear text? To encrypt or not to encrypt? That is the question. So with our legacy crypto maps, the answer was, well, if traffic is going out of an interface and there's a crypto map, You check against the crypto ACL, and if it matches, you encrypt it. With DMVPN and FlexVPN, if traffic is being routed out of a tunnel interface or a virtual access interface that has a tunnel protection profile for IPsec, then yes, you go ahead and encrypt that. But now with Getvpn, we have a different paradigm. With Getvpn, the answer to the question of should I encrypt or not encrypt, it's based on policy. So we could say, for example, that our policy is to encrypt everything from the 10/8 to 10/8. And let's call that our Getvpn policy for a moment. And so now, as R1 is forwarding traffic, it takes a look at those packets and says, okay, hold on a second. This is coming from a 10 network. It's going to a 10 network. I'm going to go ahead and encrypt this. And again, it's going to leave that original IP header intact. So anybody in this intermediate network will see it's from 10.1.1.6 going to 10.3.3.9. But because it matched the policy, R1 is going to go ahead and encrypt that using the traffic encryption key that's associated with the security association that it has for Getvpn, and then forward it. So intermediate routers, they can forward it. If it was multicast and intermediate routers needed to forward that to multiple destinations, they could. And in the case of our unicast traffic, when R3 sees that and it sees, okay, this traffic is coming from a 10 network to a 10 network, it's also going to know, oh, you know what? I need to decrypt this. So the layer 4 protocol in that packet is going to be ESP. It's going to identify the security association based on the security parameter index in that header. And then R3 will decrypt that traffic and then continue to forward it on to its final destination. Another part of our policy for Getvpn could be what type of encryption are we going to use for the IPsec. Are we going to use AES 128 or AES 192 or AES 256? And whatever we decide on as far as our policy, all the group members, because they all buy into it and agree to it, are going to go ahead and use that policy. We now have a simplified, unified policy that we can push out and everybody's just going to buy into it. Now, you might be saying, hey, Keith, that sounds pretty good, but how do we get the ball rolling? For example, where do we define the policy for Getvpn regarding the traffic that should be encrypted versus traffic that shouldn't be encrypted? And where do we go to define the IPsec protocols that we should use for our group members as they're doing the encryption? And the answer is we're going to use a centralized device called a key server. And on that key server, here's what we get to do. On the key server, we're going to go ahead and create our group policy. And when I say group here, I'm referring to Getvpn group policy. So that would include what traffic should we encrypt. And that can be done by using an access control list on the key server and say, okay, regarding traffic to encrypt or decrypt, let's go ahead and match this ACL. And in our topology, if we wanted to encrypt traffic from any 10 network going to any other 10 network, the access list would simply say permit IP traffic from 10 going to 10. And we'd make that as part of our group policy on the key server. And the key server can push that policy out to the group members. Now our next challenge is like, who are the group members? And so I'm going to use the acronym GM to refer to group members. And the answer to the question, who exactly are the group members, are any devices that have registered and authenticated with the key server. So in our topology, we're going to bring up a new router. Let's say it's R5. And let's say R5's reachable address is 5.5.5.5. And let's also imagine that we've got full connectivity between R1, R2, R3, and R4 to all of the subnets, which we could do with, for example, a routing protocol, as well as the 5.5.5 address that is located on R5. And with FlexVPN, we're assuming that we have full connectivity and reachability to all of our networks, because we're not going to be hiding those original IP source and destination addresses, so we're assuming full connectivity. So if R1, R2, R3, or R4 want to become group members, they need to first of all be configured to be told, okay, who is the key server? So we would tell R1 that the key server is 5555. We could also set up backup key servers for fault tolerance purposes. And what R1 will do, it'll go ahead and register with that key server. Now R5 acting as the key server and R1 as a group member. Now the challenge for the key server is, how does it know that R1 is a valid group member, that it deserves to be a group member, that we should be handing out policy and the keys involved to that group member? How does it know? And the answer is the group member and the key server are going to authenticate each other. And instead of creating some new way of doing that, we're simply going to go ahead and use IKE. And the most traditional way is using IKE Phase 1 from good old IKE version 1. Which goes back to the crypto ISAKEMP policy and the haggle regarding the 5 elements they need to negotiate. So if they negotiate, they're going to use RSA signatures for authentication. That's great. Or if they negotiate with each other that they're going to use pre-shared keys for that IKE Phase 1 authentication, that's fine too, as long as they have compatible keys set up for the authentication piece of IKE Phase 1. Now, if that registration is successful, which implies that the authentication was also successful, the key server can then go ahead and push down the Getvpn policy to R1, which would include the information such as which traffic should you be focusing on to encrypt and decrypt respectively. It would also have details regarding the key, specifically the traffic encryption key, that R1 can then use for the respective encryption and decryption. And with that key, we'd also have the associated group SA that was going to be used, the security association, for the encryption and decryption. And the communication of all that policy from the key server who has that policy down to the group member who wants that policy is done using the protection of the IKE v1 tunnel. And that way anybody eavesdropping on the network won't be able to discover what the keys are and the SAs are and the policy is. Now the challenge is, what if we change policy on the key server? So in the past, for example, we have traffic being encrypted from the 10 anything going to 10 anything. What if we want to add additional policy? For example, maybe we want to include 172.16/12 going to 172.16/12. That new information would need to be pushed down to the group member so he has the latest and greatest information. Another time for sure that we're going to need to have updated information on R1 is what happens if the traffic encryption key, which is being used for IPsec, what if that is about to expire? So let's say we have a lifetime of 1 hour and the time's running out on that security association. Well, R1 and all the other group members, they need to have an updated new traffic encryption key. So to facilitate that, we have something called a rekey. And a rekey is exactly what it sounds like. We're simply going to have the key server create a new key and then go ahead and push that down via a rekey to all the group members. And the good news is there is some overlap. So we might have, for example, a small window of time. Let's say, as an example, 1 minute, where the old security association, the group SA, is still valid, and the new SA is also valid. And that would give us a little wiggle room between, for example, R2 and R3 that may be a few seconds off for their rekeying if we want to make sure that traffic that they're encrypting is still accepted. And that's what rekeying is all about. Now, even though the initial registration and the initial push of the policy from R5 down to the group member is done under the protection of IKE version 1, Getvpn does not leave that IKE v1 tunnel running. So the IKE version 1 tunnel was negotiated using UDP port 500, which is the same protocol and port that IKE v2 also uses for its negotiation establishment of its IKE v2 tunnel. But after the initial registration, both the key server and the group member are going to allow that IKE phase 1 tunnel to go ahead and expire. For Getvpn, after that initial registration, we no longer need that IKE phase 1 tunnel. However, what we are going to need is we are going to need some kind of secure communication for the rekeys that happen. And when the rekeying happens, it uses UDP port 848, which is a separate security association just for rekeying. So after a period of time, we may do a show crypto ISAKEMP SA, and it's very likely after a period of time that we're not going to see any IKE phase 1 security associations on a group VPN router due to the initial IKE phase 1 timing out. But we would expect to see for the rekeying a security association with 848. And that can also be seen with a show crypto ISAKEMP SA. And the output of that will show us specifically that that is a rekey security association. Now there's one other key I want to talk to you about, and that is a key that's used just for rekeying information to protect the data as it goes between the key server and a group member. And it's called the key encryption key. So if we go back for a moment to the traffic encryption key, if we have R1 sending a packet over to 10333, that transit traffic, the user traffic, would be encrypted using the common traffic encryption key that all members of the group have. However, when the key server is communicating confidentially with R1, to keep that data secret, it's going to use the key encryption key. So when it comes to KEK, the acronym for key encryption key, that is the key that's used between the key server and a group member to keep their conversations private. And the key encryption key is going to be used very seldomly. It's only when the key server is sending policy down to a group member, which in a stable environment will happen periodically, but not that frequently. On the other hand, the traffic encryption key, if we have Bob over here, and we have Lois over here, and they're sending traffic back and forth, the traffic encryption key, which is used to protect the traffic between Bob and Lois, that's going to be used millions and millions of times. Once for every packet that's going between Bob and Lois, if our policy says encrypt traffic between 10 anything and 10 anything. We're going to start off on the key server itself, and we're going to create a very simple IKE phase 1 policy And to do that, we'll go into configuration mode. Let's call this crypto ISAKMP policy 10. For hashing, we'll use SHA-256. For authentication pre-share, for Diffie-Hellman, we'll use group 14. For our lifetime, I'm going to set this really, really low, 180 seconds, and we'll use AES-256 for encryption. And you might ask, why, Keith? Why set the IKE Phase 1 lifetime for 180 seconds? I mean, that's going to be over in 3 minutes. And the reason I set this artificially low is I just wanted to make sure that we could both see that that IKE Phase 1 tunnel can time out. It's not going to affect anything. And if we have future rekeys, it'll go ahead and create a rekey security association for those subsequent rekeys between the key server and the group member. I think that verifying our IKE Phase 1 policy is a great idea, so we'll do a show crypto ISAKMP policy. And after all the IKE v2 stuff we've been doing, it's now difficult for me to type in ISAKMP compared to IKE v2 just due to the repetition. And because we are using pre-shared keys, we also need to specify a pre-shared key. If we knew exactly who our group members were going to be and there was a limited number, we could also specifically put in the address for each of those peers on separate lines to go ahead and lock it down and make it a little bit more secure. But for the best security, we should really use RSA signatures for the authentication instead of pre-shared keys. For the rekeying that's going to happen between the key server and the group members, the key server is going to need a public-private key pair, an RSA key pair, for that authentication, which again is separate from the IKE Phase 1 authentication. So we're going to create a public-private key pair with crypto key generate RSA general, meaning we have general purpose keys. And I'm going to give it the label of Getvpn with a modulus of 1024, and I'm going to specify that this is exportable. Now, in a single key server environment, the exportable piece isn't that big of a deal. However, if we have two key servers, which they call cooperative key servers for fault tolerance, both key servers are going to need to have the same RSA public-private key pair. So by adding the exportable option when we create the RSA public-private key pair, we can go ahead and export this key pair off of R5 and put it on our second and redundant key server. So they both have the exact same RSA public-private key pair. Now, because this is the key server, we're going to go ahead and push policy from this device. Let's create an IPsec transform set. We'll call it our-t set. And let's use AES 192 and SHA-HMAC as part of that IPsec transform set. Next, and you're going to love this, we are going to leverage something we already know, and that is a crypto IPsec profile. And for this one, I'm going to name it something unique so that we can pick it out, called GDOI-profile. Again, GDOI standing for Group Domain of Interpretation that all of our group members will buy into. But short of that creative name for the actual profile name, it's just an IPsec profile. In that IPsec profile, let's go ahead and tell it that we want it to use the transform set called our-t set. That's the transform set we just created. So that once again is another command set that we're already familiar with, nesting the transform set as part of an IPsec profile. And for this demonstration, what I like to do with you is let's go ahead and set the lifetime for the IPsec tunnel to be 300 seconds. Now, it doesn't like that. It took the command, but said, hey, you know, a lifetime of 300 seconds for the IPsec Security Association, that's not very long. You're going to have that thing rolling over every 300 seconds. And to that I say, yes, because in this demonstration, I want to share with you and do some show commands with you, where, with setting a very short lifetime for that SA, it's going to trigger rekeying more often, so we can see that activity and verify that activity between the key server and the group members. So in a production environment, we very likely would not set the IPsec Security Association lifetime to such a small value. Next, we have a new command that we have not seen, and that is crypto GDOI, which stands for Group Domain of Interpretation group, and then I'm going to go ahead and name this group our-Getvpn. Now here's the play-by-play for this GDOI group. The configuration of this GDOI group can be a little confusing if we don't pay attention to the prompt that we're currently sitting at. So for example, we typed in crypto GDOI group, the name of our group, and it put us into group configuration mode. However, within that group, we're also going to define a server. In the case of R5, that server is going to be local at the IP address of 5.5.5.5. So as we start defining that server, this prompt is going to change to indicate that we are in this server subsection of the GDOI group. Another aspect that we're going to configure is the security association. At which point this prompt is going to change again to let us know that we are in the SA subsection of the server subsection of the GDOI group. And again, paying attention to this prompt is going to be our visual clue as far as which section that we're currently in. And it's in this SA subconfiguration area where we're going to point to our IPsec profile, which is this guy right there. We're going to have a match statement pointing to an access control list, which indicates to the group member which traffic it should be looking for to do the appropriate encryption of that traffic. So I want to primarily just have you pay attention to these prompts as we go through each of these subsections of GDOI group configuration. For this group, we're going to set up an identity number. And the syntax for that is identity number and then the number you want to choose. Now this identity number needs to match on the key server as well as on the configuration of the group members. Next, we'll define the details about the key server itself by typing in server space local. And you'll notice our prompt change. Now we're in this GDOI local server subsection. I'm going to tell R5 that for its GDOI communications with the group that it should use its local address of 5555, which is reachable by each of the members of the group, and it happens to be the IP address that the group members are going to point to for their initial registration with this key server. Now as time passes and we need to do rekeying, or if we need to do a rekey because we've changed our policy on the key server, there's two different methods that we can use to deliver that updated information to our group members. One is we could use multicast traffic, which is enabled by default. And if we use that default, we'd also have to specify the specific multicast group that we want to use to deliver that rekey information. And so that would be helpful in a really huge environment where we had lots and lots of devices, because the key server wouldn't have to go ahead and send out individual updates and individual rekeys to every single group member. However, another option is to specify that we want to do rekey based on unicast. And one of the reasons I like the unicast option is that the key server is going to send an update and it's waiting for an acknowledgement back from that group member just to confirm that the group member got it. Now, if the group member in unicast doesn't respond, the key server can do some retransmits and some retries to get that rekey information down to the group member. Now, if there's an extended problem where the key server and group member can't communicate with each other, group member will do a brand new registration up to the key server to get the ball rolling again. However, we should not, in a working, stable environment, we shouldn't see new registrations happening periodically. We should just see rekey messages happening. Because if registrations are happening, instead of rekeying, there is something wrong with our rekey configuration. Either the IP addresses are off or the multicast is not enabled correctly, and we want to dig in to troubleshoot that problem. Now, there are two keys that we're dealing with. We have the traffic encryption key, which based on this Security Association lifetime for the SA tunnel is going to be 300 seconds. And that'll be applicable for the traffic encryption key, the TEC. We can also specify a lifetime for the key encryption key that's used between the key server and the group member. To specify the lifetime for the key encryption key, we can use the command right here, rekey, lifetime, seconds, and I'm going to put this guy at 600. That way, when you and I look at the configs, when we see 300, we can realize, oh, that's the IPsec Security Association lifetime. And that's applicable to the traffic encryption key. And when we see the lifetime of 600, we'll realize, oh, that's the lifetime for the key encryption key. So in this case, the actual key used to encrypt traffic from the key server to the group members, that is going to change every 600 seconds. So in effect, a rekey can happen for three different reasons. Number one, we have a policy change, where we need to push updated or new policy down to the group members from the key server. Second, our traffic encryption key could be about to expire, and we want to push down a new key. And third, we could have our key encryption key that's about to expire based on this lifetime. And that would also trigger a rekey, because the key server wants to tell that group member what the new key is it should use between the group member and the key server, so that the key server and the group member can securely continue to communicate with each other regarding any of these three elements that might be changing. And what the retransmit offers us is this. If we did a rekey, for example, with a group member, we're using unicast and we didn't get an acknowledgement back, go ahead and wait 10 seconds and then try again. And then the key server says, well, how many times do you want me to keep retrying this? And the answer here, based on this configuration, is we want to try it 2 times. Now, during the initial registration between a group member and the key server, they're going to use IKE version 1, phase 1, for that protection. However, for rekeying, we're going to use a public-private key pair that's sitting on the key server, and to specify the exact key pair we want to use, the syntax would be rekey authentication my pub key RSA, and this last piece is the actual name that we gave our public-private key pair. We called it Getvpn, but if we'd called it r5.cbtnuggets.com or whatever label we assign to it, that's the label we would put right here as well. And as far as troubleshooting goes, that's one of the first things I would look at. If the rekey is not functioning correctly, I would want to make sure that the local server has its IP address specified that it's going to use to initiate the rekeys back to the clients. And I'd also want to make sure that they had created a RSA public-private key pair just for the purpose of rekey authentication, and that they had referred to it correctly with this command rekey authentication mypubkey RSA and the label of that key. Next, we get to go into the subsection for the IPsec SA. So I'm going to call this SA IPsec1, and you'll notice our prompt changed. So we have GDOI SA IPsec. So we started off at crypto GDOI group, and then we went down to server, and now we're in IPsec. Inside of the details for this IPsec Security Associations, we're going to identify the IPsec profile that we want this group policy to go ahead and use. And the syntax for that is profile and the name of our IPsec profile. So this IPsec profile that we just pointed to is this IPsec profile we created right here. The one that we had previously injected with the transform set called our-tset. Next, in this SA subcomponent, we're going to identify the access control list we're going to use for our group members to do their decision making on regarding whether they should encrypt or not encrypt traffic. So in our example, we're going to point to access list 101. The syntax is match address IPv4 and then the access list number. Of course, we'll also need to create that access control list to make this a working configuration. I'm also going to specify the replay time window size of 5, which is 5 seconds. And one of the anti-replay features that's built in to Getvpn is that there's something called pseudo time. Now in Getvpn, if we have R1, R2, R3, and R4, we don't really have a good opportunity to count packets as they go between peer X and peer Y. So we can't use that same type of counter or sequencing for anti-replay protection in Getvpn. So instead of doing that, they use something called TBAR, which stands for time-based anti-replay. And what happens is the primary key server, in our case we only have one key server, R5, it's going to create something called pseudo time. And that pseudo time is pushed down from the key server to the group members. And it's updated periodically. I think the update is like every 7,200 seconds. The key server will send an update regarding here's the current pseudo time. And in each packet that's encrypted by a group member, it's going to include the pseudo time in the packet. So R1 as a group member, if it's sending an encrypted packet and R3 is going to decrypt it, it's going to look at the pseudo time inside the packet. So if we set the anti-replay window to 5, that basically means that the timestamp, the pseudo timestamp in the packet that R1 sent cannot be more than 5 seconds off the pseudo time that R3 currently believes it to be. Because if it's outside of that window, it's going to go ahead and say, wow, this packet is too late. Which could help mitigate someone who has captured a whole bunch of packets and is later attempting to replay them. So again, that pseudo time is not based on having accurate NTP between R1 and R3. That pseudo time is coming directly from the primary key server, and it's used as anti-replay protection. So to exit out of this, let's go ahead and type in exit, and that takes us out of SA configuration mode. I'll hit the up arrow key. We'll do exit again. That takes us out of server configuration mode. And exit one more time takes us out of crypto GDOI group configuration mode. And that reminds me of the joke about 2 wrongs don't make a right, but 3 rights will get you back on the freeway. Well, 3 exits will get you out of the deepest part of GDOI group configuration mode. As part of our group policy for the IPsec SA, we pointed to access list 101, so we need to create access list 101. And in our topology, let's say any traffic from 10 anything going to 10 anything, that will be a match. And so we'll put that information into access list 101. IP access-list extended 101, and we'll say please permit IP traffic from 10 anything with the appropriate wildcard masks on the last 24 bits going to 10 anything with the appropriate 3 octets of wildcard masks for the back 24 bits. And now we have our access list configured that'll be part of our Getvpn policy. The last thing I'd like to do is let's go ahead and take R5 and put all of its interfaces into OSPF area 0. And the reality is, in my little cloud network on this topology, it's really just R5 with 4 interfaces connecting R1, R2, R3, and R4 together. So by enabling OSPF on this core router R5, and if we also enable OSPF on our 1, 2, 3, and 4, we'll have our full routing capability between any of the subnets. Which again is important for Getvpn because we're not going to be tucking in and hiding any traffic inside tunnels. We're going to leave that original IP address on every single packet. So let's go to our group members and configure them. We'll go to R1 first, and on R1 we're going to create a compatible IKE Phase 1 policy. So to match what we have over on R5, which is our key server, we're going to type in crypto ISAKMP policy some number. Lower is better as far as higher priority, and we'll specify the encryption, the hashing, the authentication, the lifetime, and all the other details regarding the IKE Phase 1 negotiations to make it match with the key server. Also, because we're using pre-shared keys, we've also identified the pre-shared key that matches the one that R5 is going to be using. And for the address, we put in a wildcard. Now, in this example, our only concern is authenticating with the key server, which is R5. We don't need to worry about doing direct authentication with R2 or R3 or R4 because we're not building IPsec tunnels to R2, R3, or R4. With Getvpn, there are no tunnels set up between the group members. They're simply all using the group domain of interpretation, the common SA, following the policy that they received from the key server. Next, on this group member, let's create a crypto GDOI group, and we're going to call it here our-getvpn. Now this label that we've assigned, or this name that we've given to this GDOI group here on this group member, the actual label name isn't the critical part. Of course, it's the ingredients that go into this group on the group member. That's the part that's important. The first thing we're going to put in is the identity number that matches the identity number that's being used up on the key server, with the syntax identity number 6783. Now, unless R1 is a psychic and knows exactly what the IP address is of the key server, we need to tell it. To use that, we'll use the command server address IPv4 5.5.5.5, which is the reachable address of the key server. Now, to implement group encrypted transport, or Getvpn, on the group members, we are going to create a crypto map, and we are going to apply that crypto map to the interface on the group member where it's expected to encrypt and decrypt traffic. So the syntax for creating a crypto map is crypto map, the name of our map, the sequence number, because we might use one crypto map with several different peers. But check this out. Instead of using the traditional IPsec-ISAKMP, which allows us to help dynamically negotiate and build the tunnels, we're going to use this option right here called GDOI. So we'll type in GDOI, press enter, and the only thing we need to do in this crypto map is point back to this GDOI group that we just created. So our GDOI group has the identity number, it has the IP address of a key server, and we're simply putting that into our crypto map, which we will apply to the interface. So the syntax to apply that group is set group and then the name of our GDOI group. And then in interface configuration mode, we'll type in crypto map and the name of that crypto map that we just created called getvpn-map. Now take a look at this message we received. It says that registration to the key server at 5.5.5.5 is complete for group our Getvpn, which is this group right here, which was also tucked into our crypto map, which we applied to our interface. We have another message indicating we had success in installing the policies from that key server. Now on this interface, if we wanted to as well, we could also set the IP TCP adjust-MSS to 1360 just to help avoid some fragmentation problems that might come up. And that again would depend on your network. But it is an option you might want to consider as you're looking at performance and fragmentation on your network. Hey, let's also go ahead and add R1 and all of its interfaces into OSPF. And when we do that, it should be able to form an adjacency with its next buddy over, which in this case is R5. R5 is the cloud that's gluing R1, 2, 3, and 4 all together. The configuration on the other group members, R2, R3, and R4, is going to be identical. Now on the key server, if we had a policy change and we wanted to force an immediate rekeying for that new information, what we could do is the command on the key server crypto GDOI KS rekey with the option replace -now. Now it's saying here, hey, we haven't had any policy changes since the last time we pushed out policy to these guys. Are you sure you want to do it? I'm going to say yes, and that's going to force a rekey to all of the group members. So it sent it from our source address of 5555 based on how we configured this key server. And if we take a look at R1, it says that the key encryption key as well as the tunnel encryption key were updated, and the policies were also successfully installed. Now, because they hadn't changed from what they were like 5 minutes ago, it's the same exact set of policies. And if we look at R2 and R3 and R4, they're all reporting very similar information. We can issue a Getvpn specific command of show crypto GDOI, and that is a fantastic command. Look at all the information it's sharing with us. The group identity number, how many current group members have registered with this key server, Here's the group rekey lifetime. That's for the key encryption key that we set. And the remaining lifetime is 514 seconds. And this time to rekey implies that the key server is not going to wait till it gets to the last 4 seconds and then try to do a rekey. The key server is going to give itself some wiggle room so that if, for example, there's a transmission issue or we don't get an acknowledgement back, we have some time left over still to do a retransmit or a retry before the current key encryption key expires. The 10-second wait for a retransmit and the 2 attempts are based on how we configured Getvpn on the key server. Regarding our security association number 1, the lifetime we set for 300 seconds. The remaining lifetime for the IPsec SA is 215 seconds, but we are going to rekey in 99 seconds. Again, we want to do that rekeying before the existing security association and its associated tunnel encryption key before they expire. The access list we have configured is access list 101. Another great command is show crypto GDOI KS policy. So for the KEK, the key encryption key, our lifetime was set to 600, and currently the time to rekey after I typed in this command is 363 seconds. The remaining lifetime of that key is 588 seconds, but again, the rekey is going to be done a little bit early to err on the side of caution. Also, as I've been editing and going back and forth, the output that we see here is based on the time that I actually ran this command. And I point that out just to make sure that as we're looking at these numbers, if in one screen it appears that there's 400 seconds left, and the very next screen it appears like there's 100 seconds left, it might have been 300 seconds between the time I issued the first command and the next one based on live clock time. So here we have our TEK, that's the traffic encryption key. That's going to be used for encrypting transit traffic as it goes across our Getvpn network. So as we scroll down a little bit, this is the older traffic encryption key with a remaining lifetime of 24 seconds. Here's the new one with a remaining lifetime of 209 seconds, and check this out. On this latest and greatest one, it also is specifying right here the time to rekey. And the reason on the old one there was no time to rekey is because the rekey has already been done. So if we look at the overlap, if this key has already been out for 91 seconds, and the existing key is good for another 24 seconds, those two together are 115 seconds, which is roughly 2 minutes. So at least on this version of Getvpn on these routers, the default behavior appears to be about a 2-minute leeway, where a new traffic encryption key is created and pushed down to the group members and available for 2 minutes before the older key that's being used for traffic encryption, before that's completely expired. If we want to look at the access control list that's in the policy on the key server, of course we could do a show access-list and that would show us, or we could do a show crypto GDOI KS ACL, and that will show us specifically what's configured as part of Getvpn on the key server, and it will spell out the details of that access list as well. If we issue the command show crypto GDOI KS rekey, that will show us the number of rekeys sent, including the one that just happened on screen, including the rekey interval for the key encryption key, which we have set to 600 in our policy, the IPsec SA1 lifetime for rekeying, which we have set to 300, because that's the lifetime of our IPsec SA in our config. And this screen also shows us our remaining lifetime for the key and how many seconds until we're going to do a rekey based on that lifetime. So as of the moment we issue this command, 194 more seconds, and we're going to have a rekey for the KEK. And in 120 seconds, we're going to have a rekey for the IPsec SA, which is another way of saying the TEK. Because the traffic encryption key is the key used to encrypt and decrypt traffic respectively for the IPsec SA. And if we want to see information regarding who is registered with us, we can use the command show crypto GDOI KS member, and it'll give us information on our members. So R5 is saying I've got a group member at 15001 who's connected with me. They're part of that group ID 6783. I've sent 18 rekeys over to that group member, and he got all of them. And there's been 18 acknowledgments of those rekeys, which means for R1, the rekeying process has gone without any error. Now, on our group members, we also have a nice series of show commands that we can issue. For example, if we do a show crypto ISACEMP SA, that's going to show us our IKE between R1 and any other peers. If we want to see more details regarding those security associations, we can tag on the word detail, and they're both going between us, R1, and 5555, which is the key server. Now, I want to point out something interesting. This GDOI rekey implies that this is the SA4 rekeying. And take a look at the authentication, it's RSIG. Now initially, when R1 registered with the key server, it was using pre-shared keys. And initially on R1, if we did a show crypto ISACEMP essay, it would show GDOI idle as the state, meaning it's done its work, it did the registration, got the policy it needed, but the usefulness of that IKE phase 1 tunnel that was built is done because when a rekey happens, the key server is going to initiate another tunnel. And it's not our traditional IKE phase 1 security association. This is an IKE GDOI rekey tunnel. This is the one that uses UDP port 848 for its establishment. And for the authentication, the key server is using its RSA public-private key pair. And that's why it's showing up as RSIG for the authentication. So on R1, if we do a show crypto session, which we have previously when working with IKE v2, here we can verify the port that we're dealing with, which is UDP port 848. It says up-active. There's our two security associations. Now the question is, do we really need two IKE version 1 tunnels for this rekey? And the answer is no, we don't. And here we have the IPsec flow that was identified as part of that policy we got from the key server, which says go ahead and permit or match on any traffic going from 10 to 10. Another really great command is show crypto GDOI. Now we can use this on the key server as well as on the group member. So from the group member perspective, it knows that server is 5555. If we had cooperative and fault-tolerant key servers, we could have 2 key servers listed there. Our current status with our key server is registered. We got our last rekey from 5555. We've had 21 rekeys, and we've sent 21 acknowledgments for each of those rekeys. And if we scroll down a little bit more, it has the crypto ACL. That's the policy that we're going to follow with Getvpn. Traffic from 10 to 10. Here's information about our key encryption key. Rekeys are happening via unicast versus multicast. The encryption algorithm that's being used for the key encryption key is triple DES, and the HMAC method is SHA. And these are the defaults that are being used on that key server because I didn't configure any specifics regarding encryption or hashing to use specifically with the key encryption key. For the traffic encryption key, we're using this security parameter index. The anti-replay window is 5 seconds that we set up earlier. The lifetime on this tunnel is 62 seconds, and the lifetime on this second traffic encryption key is 247 seconds. So after 62 more seconds, anybody using this traffic encryption key right here will not have success, at least not with R1, because after 62 seconds, R1 is no longer going to consider this SPI as being valid, nor its associated traffic encryption key. And once this is gone, this will be the only traffic encryption key until we get close to the end of that lifetime, which will trigger a new rekey from the key server to push down an updated and yet newer traffic encryption key. Some other commands that might be useful to us on our group members are show crypto GDOI GM rekey, which is just a quick overview of the number of rekeys that have happened. Some of the commands that we've used previously in this course would include show crypto engine connections active. Now doing this command with Getvpn, the interpretation is a little bit different. These 2 tunnels are the rekey essays for IKE. And the show crypto ISACEMP will verify if those are the initial IKE phase 1 security associations. If they say GDO idle, those are the original ones. Or if they say GDOI rekey, those are the new ones. Now regarding these 4 IPsec security associations that we have in place, if we take a look at the details of those, they show crypto IPsec essay, you'll notice from this output that we have no traffic that's been either encapsulated or decapsulated over Getvpn, no packets encrypted or decrypted, which normally would be a bad sign. However, in our lab environment, that's because we're not sending any traffic from a 10 network to another 10 network. We'll solve that here in a moment. And regarding the 4 IPsec essays that showed up in show crypto engine connections active, if we have 2 current techs, meaning one that's almost about to expire and the other one that was just created, we know that for IPsec we have an outbound and an inbound unidirectional security association. So if we have 2 techs, A and B, we're going to have an inbound and outbound for each of them, but check this out. Look at the security association inbound for one of these techs, and in hexadecimal the SPI ends in 01B1, and that's for the inbound SA. If we look at the outbound SA, look at this. The last 4 digits are also 01B1. That's because it's the exact same security association that's being used for inbound and outbound. So let's send some traffic across this Getvpn network. We'll do a ping of 10.222, which is behind R2. We'll source it on R1 from 10.111, and we'll repeat it 123 times. That'll give us some very identifiable traffic patterns. And now if we use the command show crypto engine connections active, we can have a nice clean view of the hit counts for encrypted traffic, that'd be outbound, and decrypted traffic, that'd be inbound. So at the moment, even though we have two traffic encryption keys, we're only using the one for the inbound and outbound. And if we wait a moment right here, and we simply wait, and let's use the up arrow key, and if you'll notice at the moment, we only have one single traffic encryption key. And all of the pings that we did, those hit counts because they were on the old traffic encryption key, which has now been deleted based on timing out. That's no longer being shown up here. Now this message we just got that indicates there's a rekeying, if we hit the up arrow key again, it's very likely that we're going to now have two traffic encryption keys. One that's older and is going to time out first, and the other that has just been put in place. So if we do that same ping again, and then we issue the command show crypto engine connections active again. So for those pings that use the traffic encryption key, that's represented by ID 59 and 60, but eventually that is going to time out. And the counters currently associated with that SA, those will also go away. As you practice with Getvpn, you can refer to this document called Getvpn. I've included it in the Nugget Lab files for this course, and it includes the entire configuration that we've just done together, both on the key server and each of the 4 group members, which were R1 through R4. I have had a great time in this video. I'm glad you joined me for it. I hope this has been informative for you, and I'd like to thank you for viewing.